Welcome. This is the second video in the series on principles of radiographic exposure 2. In the last video, we had an introduction to computers, went over electrical components, and talked about ideas and concepts that will be needed throughout this series. In this video, we will expound the ideas explored in the last video and continue learning the base information we need to continue into digital radiography. We'll go ahead and we'll talk briefly about the history of digital imaging and digital radiology. The development of digital radiology began in the 1970s with the development of computer tomography and magnetic resonance imaging. The first CT of the head was taken in 1971. This is the first CT scanner here. The first whole body CT was in 1974. The first MRI that was taken was in August 28th, 1980 was the first MRI image taken. These were the first technologies that acquired a medical image and converted it to a display. Therefore, the patient imaging and diagnosing processes had no need for a soft copy. There was no need to have a film in the acquiring of the image and the diagnosing of the patient from the image. Films were often still printed for radiologist interpretation early on due to no central system being in place at this time for sending, receiving, and retrieving the medical images. Currently, we have a system in place that's known as PACS. We will cover that in later videos. The first commercially available computer radiography, which is CR, was developed in the early 1983 by Fuji, and this is a picture of it in the background. Okay, the processing unit, obviously not the tube and the other equipment. This was the first time general radiology exams did not need physical films to complete an exam. By the 1990s, advances in the miniaturization of electronics led to the first digital radiology systems, which is known as DR. DR may also be called direct radiology in some texts. This can be kind of confusing because there is two different processes in digital radiology, direct and indirect, for the acquisition process of the image. To minimize confusion, DR will be digital radiology, okay, which will include the umbrella of any type of acquisition process, whether direct or indirect, okay. This was not possible before because the electronics needed to be smaller than 200 micrometers, which is the limit of human vision. So digital radiology wasn't possible before because the electronics needed to be small enough, and we'll learn about why in the DR video. The first digital imaging systems were in the field of dentistry, interesting enough, and here's a picture of the first DR. So we can see that there's a display, there's a cord running that's going to collect the information, everything, okay, and this is a dental tube. Okay, a dental x-ray tube, of course. All right, and the images will be displayed here. Now let's go ahead and let's talk about the nature of the digital image. We'll start our exploration of the nature of digital radiology by talking about matrix. Matrices. A matrix is a grid broken up into rows and columns. Each column is typically labeled with letters starting with A. Each row is typically labeled with numbers starting with 1. A column is vertical, so they're up and down, okay, and then each row is horizontal, okay, so it goes like left and right. Each grid element is called a cell. The matrix does not have to have the same number of columns and rows. A matrix is described by the number of columns and rows it contains, written as number of columns by number of rows. This could be 1920 by 1080. The total number of cells in a matrix can be found by multiplying the number of columns by the number of rows. In the example given before, it would equal 2 million. Okay, 2 million plus individual cells. Okay, is what this matrix would be made up of. We could call this 2 megapixels. Okay, so if this was an image, we can call it 2 megapixels. This is also the formatting of what is 1K or full HD. Okay, video or an image, or 1080p typically. This is a 16:9 ratio. So we can find the ratio by, we can divide this by this. Okay, it would come out to a decimal 1.777 repeating. That's the same value as 16 divided by 9. Okay, so it's, if there's 16 rows this way, there's only 9 going down. All right, there happens to be 1920 going this way and 1080 going down. We'll continue our exploration of matrix with an example, okay, what we were talking about here. So going down are the columns, okay, and you can see they're labeled starting with A, B, C, D, and then the rows, okay, go down this way. So there's 1, 2, 3, 4, and each one of these is a cell that we talked about of the matrix. And so this one cell is A1 and B1 and C1. So you can see how each cell is going to have its own unique identifier for the location it is in the matrix. Okay, this would be a 4x4 matrix, 1, 2, 3, 4 by 1, 2, 3, 4 of what's visualized here. Okay, but each cell has its a specific location based on this number value. Okay, and it doesn't have to necessarily be A's and 1's and stuff. Okay, the system's going to have its own way of labeling it, but for our purposes, columns are letters and rows are numbers. The matrix shown is a 4x4 matrix, as we talked about. It contains 16 cells. The labeling of the matrix is useful in digital imaging for location, as we talked about, manipulation, and value assignment. If you notice in the matrix example, each matrix cell does not have to be a square, but it can be a square. So if we noticed the example before, they were more rectangular here, okay? And then the one on the right, these are squares. This is due to the field of view sizes being different. This is due to the field of view sizes being different. The equation that relates matrix and field of view together is the cell size, so the size of the cell, is the field of view, so the length going this way, by the matrix. So there's 4 cells going this way, and what the length is, and that's going to determine how long this is. It's going to be the same for this side too. Okay, so the cell size going this way, the field of view here to the matrix. It is obvious that even though the matrix sizes are the same in the two examples, so each one is a 4x4 here, and the vertical length is the same, so this length is the same, the horizontal length is not. The length here is different. So this field of view, okay, this length of this matrix, okay, is different, okay, but the matrix is the same. It's still a 4x4 matrix here. So these cells are going to be longer, okay, this way. So it's going to be more rectangular than this one is. The two matrices above actually are 3.3 inches. Okay, so this is 3.3 inches long and 1.59 inches, okay, tall, and 1.59 by 1.59. This is a 4x4 matrix. The sizes are the same. Okay, the lengths are the same here. So these are going to be perfectly square cells. Okay, where this one's going to be more rectangular. The same number of rows and columns in each cell on the right as on the right and left squares. Right? In radiology, the matrix size is set by the system. This is almost always a standard size. In digital radiology, the matrix size is usually about 2,000 by 2,500 cells. some systems may have different matrix sizes. Let's look at a table of some standard sizes in different modalities. So CT, the matrix size is 512 by 512. This is an extremely standard matrix size for CT. This is what all CTs are taken at. Nuclear medicine being a functional modality, there's several different matrix sizes that can be used depending on the anatomy that's being looked at. Sonography is 512 by 512. MRI can be 256 by 256 or 512 by 512 depending on the anatomy that they're looking at. The smaller matrix sizes that could be utilized can speed up acquisition time in these modalities. Mammography is 4,000 by 5,000. Typically, it's much larger. There's many more cells. Okay, so the spatial resolution is much higher than in digital radiology. Typically, in mammography, you're looking for very small, either lesions, calcifications. So you need that high spatial resolution to see the small details. PET scan can have two different matrix sizes as well. We learned a lot so far about matrices. How does this all relate to radiology? First, let's learn about photography. In non-digital photography, the light during the image acquisition exposes the photographic film, and the image information is on the film until it's developed in traditional film imaging by chemicals, the chemical process, okay? And so the light that exposes the film is a continuous image, making it analog, as the film is exposed completely with no gaps in information. A digital image is a grid of cells. Each cell is given a discrete value or values based on the average, maximum, minimum, depending on how the system architecture is and the software algorithms utilized. But each cell is given a discrete value of information from the subject in the location the location that the cell is located. So each cell has a value placed to it or multiple values placed to it. Here we're going to look at how this happens. So as the information is coming in from the source, this can be a light source, and this could be a digital camera element here, or this could be an X-ray source. For our purposes, of course, we want to look at an X-ray source. So we imagine that this is the X-ray source coming here. This is the area being looked at, okay, the patient. So this information that's being gathered here from the anatomy is going to land on these cells. All right, and for our purposes, these cells are the detector cells or the DELs. This cell here would be in our location system would be A, B, C, 1, 2. So this would be C2 would be this cell right here. And the information that from this example would be purple. When the matrix of an image is displayed on a monitor, we can call it a pixel then at that point. So the monitor displays pixels. Pixels is going to be utilized in text in different ways. They're going to use the term pixels for different for just describing a cell of a matrix in any way. So for my purposes, when we're talking about the matrix, it's a cell. Okay, this is a cell. When it's being displayed, it's a pixel. The pixel value, so a pixel is the smallest single component of a digital image. In fact, the word pixel comes from the combination of pix, meaning from pictures, and L for element. A digital image is a matrix of values. Inside each cell, a value or multiple values is assigned to each cell, as we talked about before. The data that makes an image file contains the location and the value of every cell in the matrix that makes up the image. So the data of an image file, which could be a X-ray, it contains the location and the value of every cell in the matrix that's going to be the image or the X-ray. And as we've seen here, this is purple. Okay, so this is C2 and it's purple. The values of purple, since it's a color, we need 3 different values. Red, green, and blue value can make any of the colors that can be utilized. So C2 would be this value that was stored, and then R123, G30, G73, and B164 is this value right here. For all the other cells, if we had different locations, different values, we could create a whole picture from this. There are several different matrices involved in image acquisition, processing of the image, and display of the image. For the display of the image, I like to say it's a pixel. It's a pixel on the screen. Up until that point, they're just different matrices that can be manipulated and processed. Okay, and in the upcoming videos, we'll discuss how those things happen. We'll go ahead and we'll continue to talk about pixels. Pixel values are discrete. This allows manipulation of the image. In radiology, each pixel value represents a brightness. So for a colored image, we need 3 different values. We needed the red, the blue, and the green, as we discussed earlier with the purple. In radiology, we only need 1 value. That value is going to relate to the brightness of that cell. We can either perceive it as a white, some range of gray, or a black, and that's only as we perceive it, the brightness level in the cells. In order to achieve this discrete value, digitization of the analog X-ray signal must occur. Digitization is the act of rounding off the signals received by the detector to values that are whole. So we can't have values that are like analog, that are in between the whole values, because the electronics don't understand how to do that. Okay, so it has to be a whole number. It seems to be less accurate, however, it can be more accurate. As long as the discrete units are smaller than the human eye can detect. So smaller than the human eye can detect, as mentioned earlier in the video, in electronic size mentioned, that has to do with the spatial resolution of the human eye. This is the contrast resolution of the human eye. So as long as the discrete units are greater than what we can distinguish with the human eye, the rounding off isn't an issue, because physically people can't tell the difference in the different grays or the different blacks or whites. Digitization requires an electronic device called an analog to digital converter. Before we get into the steps of digitization, there are some terms that will come up that we need to be familiar with. So, and we may have already used the terms here and there, but pixel is a 2D representation on a monitor or display of an image. Voxel is a 3D pixel, so a voxel has volume to it. And in this example here, all this that's going through here, so all the information that's being collected from this little stick, okay, if there was a little thickness to this, let's imagine, all this information is going to be represented on this 2D plane. So this would be a voxel, okay, with this thickness here. Voxels are more so used in CT. where there's a slice thickness and a X and Y, okay, thickness to each pixel. However, it can be thought of in radiology in this way, where the information is coming from a voxel of tissue. So it's coming from a cell of tissue that has a certain thickness as it's traveling through and hitting the detector. So that's a 3D pixel, is a voxel. A voxel is a volume pixel. Data is collected from voxels of tissues on DELs or dexels. So each one of these is like a detector pixel. Okay, a detector pixel. So the DELs on the detector. So each one of the cells on the detector is a DEL. And then processed to become pixels on the image displayed. Okay, so see, these are some of the terms moving forward that are going to come up in the future videos. Now we'll go ahead and we'll talk about digitization. Okay, so digitizing the analog image. There's three basic steps. They are scanning, sampling, and quantization. Scanning. So the field of the image is divided into a matrix of cells. An example would be a photocopier. When you put the sheet down, you open it up, and you put the sheet down on the photocopier. If you pay close attention, the scanning element does a quick couple little passes throughs. When it's doing this, it's doing a pre-copy sweep before the actual copy. It performs the function of pixel allocation and determining the size of the matrix it's going to use to scan the object. In digital radiology, the matrix is determined by the number of hardware detector elements, so the number of dexels, as we talked about, and is analogous to collimation. So when we collimate, we're changing the number of detector elements we're using. So we can be changing the matrix size that's going to be used for that first acquisition. Okay, so for that first acquisition of the image, of the patient information, which will become the image. All forms of digital imaging requires this preliminary step of formatting a matrix with designed pixel size. So all forms of digital imaging, whether it's with the phone or whether it's in radiology, requires this preliminary step of formatting the matrix size with what's going to be the final pixels. Sampling, the detection and measurement of the signal coming into the system from each cell location. So this kind of makes sense. So the word sampling just means that you're taking data in, right? Okay, so it's the detection and measurement of the signal coming from the system in each of the cell locations. And for us, it's going to be of each of the dexels. So it's the collecting of the data from the dexels. Next is quantization, is the rounding off of the analog values. So that's what we talked about before. The rounding off of the analog values to form discrete values is the quantization. Quantization, which is quantity, means a value. The values are selected from a predetermined scale of numbers called the dynamic range. So the values that are available for the quantization step comes from the dynamic range. This is done with the analog to digital converter that we talked about earlier, and it will be converted to the nearest gray value. So with that, there's a few other terms that are coming up. Okay, so bit depth, dynamic range, that was on the last one, in grayscale. So the bit depth is the maximum range of pixel values the computer or other hardware device can store. Typically the bit depth for radiology, for digital radiology, is 2 to the 14. So there's roughly 16,000 plus different values that each pixel could possibly be, okay, on the system side of things. The dynamic range is the range of pixel values, which is brightnesses, or the different gray levels, all the way from black to white, made available to build up the final image. So you would say the dynamic range of this image is such. The grayscale is the range of grays actually apparent on the displayed image. So these three things can be completely different numbers. Okay, leveling slides the displayed gray scale up or down the available dynamic range, and we'll get into leveling when we talk in the post-processing video. So grayscale is within dynamic range. So all the colors that are actually apparent on the displayed image have to be within the dynamic range, the number of grays made available to build the final image. The dynamic range has to be within the bit depth of the system. The dynamic range can't be outside what the system's capable of, the values that the system's even capable of utilizing, right? So this should make sense. So the bit depth is the system, the dynamic range is what's made available for the image, and the grayscale is what's actually available, okay? So now that we learned about matrices and how values are assigned to a cell in a matrix, let's go ahead and let's see an example. So here we have a matrix that's a 12, so there's 12 columns by 16 rows. So this is a 12 by 16 matrix. So this would be pretty low res compared to 1920 by 1080, right? But we have a values assigned to it, and if we look very closely at the values, okay, we can see that the grayscale of this image is probably going to be it's probably going to be 8 bits. It's probably going to be 2 to the 8. No value is above 255. In order to, there's a 255. And there's zeros. In order to do that, we take 2 to the 8, which is 256. We subtract 1, which becomes 255, and we're also utilizing the 0. That's where the minus 1 comes in. So from 0 to 255 is 256 different discrete values that we can utilize for each cell, and we've assigned a value to each of the cells. When we put a brightness to each cell, this image will come out. So that's pretty exciting. Alright, in the next videos we will learn the process of what happens to the remnant beam after it leaves the patient all the way to the image formation. For now, we have this value, and if we do some post-processing with things to it, which is like a Gaussian blur and other things that we'll learn about in future videos, and we take away the numbers, we get this, and I think we can make out what this is trying to be. Very low res, of course, right? But we can infer what the image is supposed to be. So that's pretty exciting here, that we can see it goes from a matrix of numbers. When we assign brightness values, we do a bit of post-processing, and we have a very low res image that comes out. With this, we can do some pretty interesting things here. This is a 42 or a 64. So there's 64 columns by 42 matrix. This is an Excel, as we can see. This is something I did. So in Excel, there's values plugged in here to each cell. We can relate that to a gray value, and we can get an image that comes out. And this is the image that comes out when we relate these cells to a gray value. This is also 8-bit too. So if you don't quite recognize what this is a axial slice of the chest in CAT scan. Here you can see the spine. You can actually see the table here in the chest cavity. Okay, this is the heart. And there's lung fields. This is very low res, again, because it's only 64 by 42, and normally in CAT scan it would be 512 by 512, so it would look much sharper where it could be used for diagnostic purposes. And with that, we can do post-processing things, we can do manipulation to it, and all these other steps, and we can just be kind of fun with it, and we can get a blue image. Okay, if we want, we can make it all kind. I can make it all kinds of different colors too. And this is just done in a spreadsheet in Excel. Through the next videos, we'll learn about processing techniques. We'll also learn about computer radiography in the next video.